All right, welcome everyone. Hope everyone's doing well, and especially if you're in Texas, I hope you're all staying cool.
Yeah.
I still get heat alerts from Austin on my phone. So yeah.
Yeah, it kind of cooled off. It's only about 900 degrees right now.
Oh, all right. Yeah, that's not too bad. There you go. All right. So we have a couple of things on the agenda today. So Cesare Grava is going to give a presentation, and then I wanted to save some time at the end to talk a little bit about the European Lunar Symposium, which was last week, and the Endurance Science Workshop, which is coming up. But Cesare, take as much time as you need, and we'll let the discussion go on. But I just wanted to mention that in case I forget about it, then someone can remind me. But yeah, so welcome again, everyone. And this month we have a presentation from Cesare Grava on the effects of realistic temperature variations and orography on the structure of the lunar exosphere. And so just a quick reminder to everyone, unless you're speaking, please put yourself on mute. And Cesare, do you have a preference about whether folks should ask questions in between, or should we wait until the end?
You can ask in between, no problem.
All right. So with that, I will hand it over to Cesare to tell us more about what he's been working on.
Thank you very much, Parvati, and thank you for inviting to give this talk here. My name is Cesare Grava, for those who don't know me. I'm a lead scientist at Southwest Research Institute in San Antonio, Texas. I got my PhD degree in the University of Padua, where there was a European Lunar Symposium last week. And then I did a brief postdoc at the University of Colorado, LASP. And now I've been here at SWIRI for almost 11 years now. My interest is the study of the exospheres, particularly surface-bounded exospheres, so exospheres that start at the surface. And the moon is one typical example of a lunar surface-bounded exosphere. So in the exosphere, particles don't collide with each other, and so the dynamics and the structure of the exosphere is given by the interaction with the surface. So this talk is about my modeling of the lunar exosphere. I wanted to study the effects of realistic surface temperature variations and orography, so mountains, valleys, etc., on the structure of the lunar exosphere. And I mean, for both condensable and non-condensable species. So the motivation, was simulating argon a few years ago, and I stumbled upon this sentence from the Hoffman et al. Paper summarizing the first results of LACE. So LACE was a mass spectrometer. It was placed on the lunar surface by the Apollo 17 mission, and it was recording the atoms coming from the sky, basically down there. And so measured for the first time the composition of the lunar exosphere, and detected argon 40 and helium, and also neon, although it was not immediately recognized. But while I was reading the review literature, I stumbled upon this sentence. So sunrise at the site is delayed. So sunrise at the site where LACE was located is delayed 8 hours by shadowing from the mountains to the east, which preclude significant local heating before this time, dawn. So the Apollo 17 was in the Taurus Little Valley. And so the fact that you have the mountains to the east delayed the dawn. And so on the particles that LACE was measuring were coming from the bayside beyond the mountains. So there is some hint that the orography in this case, the mountains, affected the structure of the exosphere. And also we know that the microtopography plays a role in the distribution of volatiles in exosphere. So two papers mentioning how these microcold traps affected the distribution of particles in the lunar exosphere. So what about the big features? Like, for example, a crater like this. If a particle hits the crater, does it have a higher chance to stay in the crater because ejected almost vertically? So this is, of course, an exaggeration. And if so, how this does change compared to a flat surface? So for the temperature variations, what I mean by that is that many researchers, including myself, have used a map, a 2D map of the lunar surface temperature to study to model exosphere. So surface temperature is really important to study the structure of any surface boundary exospheres. And so this is a map of the model I was using for the other argon paper. And this is taken from the Van measurements, but with a model to fill all the gaps. And you can see pretty coarse resolution. But apart from the solution, the map is the same. So I had my code in local time, basically. So every time a particle hits the surface, it stays there, and it is rotated towards, in this case, down by the rotation of the moon. But the temperature stays the same. But of course, this does not reproduce the variations due to the topography, for example, thermal inertia. And so look at this map instead. So this is a much better resolution, 1 degree by 1 degree. And so you can see that this temperature variation is different. So you pick 2 points on the lunar surface, maybe at the same latitude, and their thermal evolution, so the diurnal variation of the temperature is different. So in particular, you see here some like a warm spots we seem to appear in the night side. So they're not taking into account with analytical formula or just one map. So I wanted to see what's the effect of the surface temperature on this. And then the topography. So I added the topography from Lola altimeter on board LRO. This is a map of the mean, the altitude of the moon with respect to the mean radius. So it is similar, but not identical to the map of the moon, as you see with the naked eye. So you can see this kind of lower, smoother plains here, the lower altitude. Here the islands on the far side of the moon. And here this huge depression of the South Pole Akin Basin. And this is a model that, no, the map that I plug into my model. And the slope also. So slope determines the slope of where particles are ejected. And so you see around the craters, the slope are bigger, of course, because of the walls of the crater. Up to 20, even 30 degrees, I believe, about that. So not everywhere, but it's important. And so an example, so this is what the effect of the slope is on, if you use a flat moon, like I used in the past, the normal is the radial direction, basically. And so you eject particles along the normal. But if you have variation due to the slope, in this case is this sigma, then the normal is not anymore the radial direction, but it is tilted. And so the particles are ejected in a cone, which theoretically is 180 degrees, but it's more like towards the normal, which is tilted with respect to the normal, to the radial direction. And so the versor also of the ejection is also different. And so I wanted to see how this plays into account in my exospheric model. So regarding the model, this is nice, one of my favorite figures about lunar exospheric modeling by Smith and Marconi. This is pretty much what I have been doing. So I have a particle is ejected here from the surface, and then it can either escape. It's unlikely for argon, but it's more important for neon. Or it can, more likely can bounce around on the lunar surface until it is photoionized or escapes again, or it is cold trapped. And so the length of the hops is proportional to the surface temperature. So the warmer the temperature, the bigger the hops. And so that's why warmer surface tend to have a lower density in the exosphere. Yeah, so particles can be trapped through the cold traps. And we assume full thermalization of atoms to the surface. So when a particle hits the surface, it is released by an energy which depends on the temperature of the cell. And this is why the colder spots have a lower hops. So to do this test, I used 4 simulations. So one is have an analytical formula for the surface temperature, which many researchers have used, and a smooth moon. So I use this formula, and for the surface temperature, which I found on the Kinney et al. 2019 paper. So dependence of a temperature on the solid zenith angle. So in this case, you have 100K everywhere on the lunar night side, and a cosine dependence on the solid zenith angle in the day side. The next one is keep the smooth moon, but use one Diviner map, the one I use in my 2015 paper. The third one is smooth moon again, but multiple different maps. So then I plug in the maps I showed before of the actual variations of the temperature. And this is, I found that the best solution is 2 lunar minutes. So every 2 lunar minutes, I change the temperature map. And this is about, so this is 725, so on the Diviner maps. The last simulation is keep the Diviner maps and add the topography and see how the things change. So non-condensable gas. So this is just one way to check things with the published paper. So this is the density as a function of longitude or the subsolar angle, actually. So this is evening terminator, this is midnight, and this is morning terminator. The blue one is the model by Kinney et al. 2019. This blue one is the code. The black one is also my code. And I think I binned it. So the blue is just a binning of the black one. See that, okay, I was able to reproduce the published results. That's good. And now this instead is the same code, but with the Diviner map. So you can see that there is a change. So just changing the surface temperature from an analytical function to a measured temperature gives a change in the slope of the increase and also on the value. So this is the non-condensable gas, which is neon. So there's a dependence of the surface of the exospheric density with the surface temperature, so that the hops are bigger when the temperature is hotter, and the shorter hops when the temperature is colder. So that's why this exosphere tends to accumulate towards pre-dawn at the coldest regions on the moon. If you take into account the Diviner map, then you can see a steep increase and not so much change in density. And I will show you in the next few slides why. Okay, so this is the surface temperature. Okay, please ignore these features here. I guess I think it's probably an ADL artifact. And so this is a pretty dull 100K everywhere in the night side, and cosine dependence on the Saturday on the day side. So this is the density of neon for this type of map. So you have a smooth decrease here in in exosphere density, or increase actually, which depends also on the latitude. And then, so this is basically from the day side transport. Okay, so pretty smooth increase towards the pre-dawn sector. And now let's add this one with the single divan map. So now you can see some interesting structures. First of all, this the extent to which the exosphere is depleted is bigger. And then if you look at the temperature map, which is the next one, you see why. So after dusk, sorry, the temperature is still warm because of thermal inertia. So it's bigger than 100K. And this is reflected on the exospheric density here. Another thing of interest is this dependence on the latitude, which we saw even at this case a little bit, but this is more marked. And this is again due to the surface temperature. So neon tends to accumulate at very high latitudes, pre-dawn, like at 2 a.m., 1:30 a.m., which is kind of what we found with the lamp observation of helium, another non-condensable gas. And if you look at the temperature, this is why. This is very, very cold regions. You see these black spots here and here. So that is why the neon exosphere density increases there. Another thing is that you notice these spots here, which are, if you flip it between and forth the temperature, and these are due to the temperature. So there's anomalously high temperature. Well, yeah, in these craters, at least from this divan map. And so when there are, wait, no, sorry. Yes, this case. When there are warmer regions, remember the hubs are bigger, so they tend to escape this region. So these kind of rarefied regions above these warm spots. Now use multiple divan maps. So this is just a snapshot. It's closest in time as the one I was showing before. And then you see pretty much the same. You have this one? No. Pretty much the same structure as here. The only difference that this is a snapshot of a map on this particular time. And again, this is the temperature for that particular lunar phase, basically, because this is lunar phase. And I also have a movie. Let me see. I have, yeah, okay, this is not, actually, this is the one with the topography. So there is really minor changes to the density. Although you can see probably some effect of the craters here. But the overall structures is mainly dependent on the temperature, as expected. And you can see these black spots here are, in this case, I'm using a grid which starts at the lowest point of the moon and has like, I think, 12 kilometers, no, was that, yeah, 12 kilometers about altitude. So some of these craters are still entirely occupied by the rock. So that's why they show up as black. And I think I have also a movie. Yeah, okay, so this is the topography I'm using again. So you can see some correlation with these features here. And this is a movie of the exosphere. So again, you can see basically at each local time. So you see, for example, this is like, let's follow this point, which is 4 a.m. maybe. So it's a higher density at the high latitudes, but there are dependencies on the phase of the moon based on which feature is at that local time, which I think is very interesting. Yeah, so also these variations in the density due to the temperature. And also, this is a nice view. So this is a view from the South Pole, where this interesting shape is of the South Pole Lake basin. So we're looking at the South Pole, and look, these are the looking to the the three amigos here. So you're looking at the Earth is up, and you're looking at the South Pole. So you're looking at the South Pole of the Moon. You see the South Pole of the Moon here, and the Earth here, which is Antarctica, of course, if you look here. And so now let's overall surface temperature and exothermic density of this region. So interestingly, the exothermic density is highest at pre-dawn and high latitudes. And this is an example of surface temperature. So again, this gas, neon, is mainly dependent on the surface temperature. So again, you know this white, I think it is like again ideal. Oh, one thing to notice is that look at this spot here where I'm a cursor. This is like a warmer region in the night side temperature from the Divine map. And in fact, it shows as a hole in the exothermic density, which is again an effect of the lunar surface temperature on the exosphere. Now go with the argon condensable gas.
Hey, Cesare, sorry to interrupt.
Again, I move directly to this view because I think it's important. So it's
Hey,
it's
Cesare, could I ask you a question really quickly? Yeah. So on the previous slide, could you explain again what the so I guess on the earlier map it was the black pixels, and here it's like the dark blue pixels. What are those again?
This one?
No, so the like you know in some regions it looks almost like there's no data there.
Oh yes,
yeah.
So like this, for example.
Yeah.
Yes. So this is a view of the entire southern hemisphere, and I divided my model in grids in my grid in altitude bins. So we are here looking at the first altitude bin, which is between -8 and +4 kilometers with respect to the lunar mean radius. So there are regions which are higher than that, and so in this case, it's occupied by rock. So that's why they are missing data. So I'm showing just the first latitude bin, and so we shows these are just rock basically. It's not yet exosphere.
Got it. Thanks.
Okay, sure.
And also, Cesare, what is that apparent spiral feature that we see coming from near the pole, then moving down to low latitude? What is that actually?
This white one? Yeah, I think it's an artifact of the IDL visualization. I have to understand why. I mean, yeah. So, but this is, I believe, is an artifact.
I think it has to do with the, like it shows up on the temperature bar as well. So I think it's just this temperature bar has a white line at 90-ish, 95-ish Kelvin for some reason. So I think that is actually an isothermal line being projected. But we haven't looked into why the bar has that.
Okay, thank you.
Okay. Yeah, so looking for the argon again. This is so condensable gas. So again, it stacks, unlike a neon, it stacks to the lunar surface, and then it is suddenly released when the surface warms up. So, unlike a neon, where you see this build up of neon in the pre-dawn sector, like 2 a.m., 3 a.m. For argon, you see the maximum density is after dawn, between 6 a.m. and 7 a.m. And you can see the effect here. So this is post-dawn. And again, very little variations with the topography. But you see a variation with the temperature, which is so, well, okay, the bulk, the dawn bulge is due to particles that are being released from the night side because of the dawn is heating up the water reservoir, but also particles coming from the day side, which are moving there in this region, or moving away from the day side. So this is a correlation with the altitude. And so, of course, the altitude doesn't change because it's a view from the south pole of the moon. And you see that there's really no major change in the altitude, in the exospheric density with the altitude. The interesting thing is that when you look at the number of the subatomic particles and surface temperature. So on the left, I have the number of test particles, which I have yet to convert into atoms per square centimeter. But this number of test particles are absorbed at the surface. And these are proxy for the areal density. So this is interesting. So you can see that, okay, this whole area is the night side. And you can see how the number of test particles they're all in the night side, but they change location with the topography. So for example, okay, look at here, this big blob, black, that's where there's an unusual spot unusually warm spot in the night side. And there, of course, results in this region being depleted by particles because they just are rejected faster. And also, the one thing I'm interesting is so this region here seems to have a higher concentration of density overall. And okay, looking here, we're looking this quadrant where the temperature is pretty much stable between 90 and 100 degrees Kelvin. But this is a snapshot of the so isolated particle. They are all accumulated here in this region. And so why is that? So if you look at the altitude map and you go back and forth, you see that these regions are all where the white spots are here in this particular region, which is the rims of craters, and which are looking towards the dawn, basically. So I'm thinking about particles coming from the dawn side, hitting there and stay there until I realize until really released later on. And if I do a comparison here, I see that even interior of the crater here, you can see some higher number density of particles here. So it's not only the ridges of the crater, it looks like also the interior of the crater are acting as a cold traps. And so I'm thinking about these are walls that are facing the dawn terminator somehow. So this might be the reason why these are particularly with higher density. But I am, okay, so I'm also try to think at why this particular region and not other regions show this pattern. Okay, so I mean, this is pretty much my talk. So the conclusion. So topography, surface temperature variation affect the distribution of volatiles in the exosphere and on the surface as well. for the exosphere, surface temperature variations are more important than topography, as we saw. And for subjects that called trapped molecules, the topography is as important as surface temperature variations. I think it should be included in any model of surface bound exosphere. And this variation in exosphere could be detectable by an adequately sensitive mass spectrometer because it's, the variations is still is not a great compared to the variations with the surface temperature. And so I'm also analyzing LADIMS data to see if we see this type of variations in the exosphere. So that would be great if you can see those in the data. Last but not least, let me take a few minutes to acknowledge my friends and colleagues who over the years have helped me doing this job. And everything you like in this talk is thanks to them too, and everything you don't like is only all my fault. So yeah, okay. I guess it. Thank you for your time. Thank you for your attention, and happy to answer any question.
Hey, thanks, Cesare. That's yeah, this is super interesting. Those maps are so nice to look at. It's yeah, I could watch those forever. Very cool. All right. So what questions do we have for Cesare? And while people are thinking, so feel free to raise a hand or put a question in the chat. While folks are thinking of questions, I'll ask one. So the maps you were showing were all at the surface density, right?
Yeah.
Is there like some certain altitude at which those topographical differences kind of blur out? Like, so for instance, you mentioned the LADI data, like would LADI see topographical effects at the altitude it was at?
That's a good question. So no, I mean, the effect of the topography and the exosphere washes out at altitude. So in particular, at the nominal altitude of LADI, which I believe was 50 kilometers, it was not visible. But so I think until 10 kilometers altitude, you still expect to see. But this is of course a very low altitude, even for LADI. I think there was some observation that low in altitude to sift them out from the data. Yeah.
And let's see, Tim has a hand up.
Yes, I meant to raise my hand, not raise my thumb. But at the temperatures that you have in the pre-dawn region, what is the scale height of the, for instance, for neon or argon?
Okay, so it's about tens of kilometers. Yeah, I don't know the exact number, but yeah. 30.
Okay, but it's still several kilometers. So I was just wondering about if you had a mass spectrometer at the bottom and the top of the human landing system, for instance, if you'd be able to see a detectable differential that would help to constrain the physics of what's going on, but I think not at such a short range.
A good point. Yeah, I mean, but there are deep craters, right? So in the map that I'm using, so the lowest point is a minus 9 kilometers. The highest point is a plus 4 kilometers. So actually plus 9 kilometers. So yeah, I mean, this needs to be very close in space probably, right? Because otherwise you have to different parameters to account. Yeah, so I was thinking about maybe some deep craters like Cabellos, which is like 4 kilometers deeper. Maybe one mass spec in the bottom, one on the top. That would give you like a 4 kilometers altitude difference.
That's an interesting point, that having astronauts deploy them to locations like that would be a lot of driving in a permanently shadowed region. So you need to envision the possibility of instruments that can be thrown,
right, exactly,
and
yes.
land on their own safely.
Yeah. And there's also some concepts about this type of hopping mass specs. I think it was one was last week at a European Symposium as well. I don't remember which one. Was just hopping from point to point. Well, in this case, you need to survive also the 4 kilometers drop. But
right, that's the problem.
yes.
And you don't want to use propulsion because then you pollute your local environment.
Exactly.
Hey, just right. So I have another question. So if you were to go to an even higher resolution temperature map, would you expect to see structure in the exosphere at that scale, or is there some lower limit of the kinds of topography and temperature variations that are different?
Yeah, so that's
that matter.
We are debating amongst ourselves, so I expect to see some effort, yes, but not really one-to-one, because I expected there is a redistribution somehow, but this is kind of what not what I'm seeing here. So I see here some effect of the topography as well, even if this large scale. This is 1 degree by 1 degree. So the equator is a 30 kilometers resolution, which is big. Yeah, I mean, I expect to see some effect. Yes, you think about it, but you know what I was trying to convince myself about this, that when you, so this is a surface bounded exosphere, right? It is a source set by the surface. And so if you go on a cliff on the earth, on a cliff, and then you, like double cliffs, you continue straight, fly, for example, the density does not change, right? But on the moon, if you have a cliff and you keep going, your distance from the surface changes. And so the distance from the source of the exotic particles changes as well. So in this case, I am thinking there should be some effect on that. Well, it is exactly the same topography reflecting the exosphere. That is, so we are debating among ourselves and the team.
So that would suggest that if you measure the density of your local atmosphere of noble gases as you approach a cliff, where you've got basically a big hole in the space, that you should see a decrease in abundance as you approach that edge, because you no longer, everything essentially flows off that cliff.
Mm-hmm. Yeah, something like that. Yes, probably not as dramatic, but yes, some difference you can, because there's sea particle moving around, right? But
right.
Yeah, there's this missing resource suddenly that should reflect in the exospheric density.
But flow is kind of the wrong word.
Yeah.
Because the whole point of why we think this might be happening is because there's no collisions to force everything to build the stratosphere, if you will.
Now we just need to persuade.
You end up just with sources and lack of sources, basically.
Yeah. Now we just need to persuade the Artemis program to have astronauts go to the edge of big cliffs. That should be easy.
While carrying however many kilograms of mass spectrometer with them.
But it's okay if they drop the mass spectrometer, because
yes.
Yeah. All right. What other questions do we have for Cesare? I guess, Cesare, not to put you on the spot, but do you have a paper on this coming up soon?
I'm preparing. Yeah, we're preparing, drafting a paper. Yes.
Awesome. Great. And I guess I'll ask one more question. And folks, if you think of questions, put them in the chat. Otherwise, you know where to find Cesare, so you can ask him later. But yeah, so I guess one last question, mostly to give other people a chance to think of questions. But so the neon plots that you showed at the beginning, where you were comparing the Killen et al. To the and so were the Killen results also a model, or is that data? And is there data, because it looks like there's a difference that you could test there?
This is interesting because this is a model that they were trying to explain the LADI and the lace measurement of neon, and but the interesting thing is that they could not match both. So because one was the LADI was doing I think coronal mass ejection, so enhanced the densities, and but in LAS was not. This was not. So what I was trying to do here is to match the shape and the density to see, okay, I'm doing things the same way, and then to see from that add the changes in the model. So the next step would be to go and try to adjust the source rate and to match the solar wind conditions, so doing the lace measurements, for example, which is like a more nominal conditions than the LADI. And the neon is also an interesting conundrum because this paper showed that they found a very high escape rate for neon, which is comparable to helium, which escapes via GC escape, which is really very interesting and puzzling. So why does neon not escape so quickly? And we don't know the answer to this question yet. So
all right, final call for questions. Okay, I'll ask one more, but so I guess this is a two-part question. So I guess one is, based on the work you've been doing so far, do you have recommendations for future either landers or rovers that might make measurements of exospheric density? And then second part of the question is there anything else you wanted to just add about all of this?
Yeah, so I from what I've seen, as I said, the density really changes very low. And I understand is the technical challenges of flying an orbiter like at 10 kilometers altitude, because there are mountains right on the moon. So, but that would be a great idea to test these hypotheses and to benchmark the model, I guess. And another one is, is Tim mentioned earlier, to have like a mass spectrometer really deep in some craters, and especially deep in narrow craters, and to see how the exotic density changes with the local time, for example. Even if it is a PSR, it'll be interesting to see the changes.
Awesome. All right. So I don't see any more questions. So I think people are still.
I see something in the chat, actually.
Oh, yes. Yeah. Thanks, Michael. So, so Rick Elphick says, cool in the sense of abundance, but the area is very blocky, but stays hotter after sunset. So I guess Rick is talking, and Rick, feel free to chime in if you're able to unmute. But I guess what Rick is saying is that, with reference to the density change when you pass over a cliff, the surface temperature at those 2 points might be different. So you might have a difference.
I was just saying the surface temperature overall at Tycho is higher after the sun goes down, because it's so blocky there. Block density is huge. So if you look at Diviner thermal inertia maps, it's one of the it's a very high thermal inertia area. So it's going to generally have I think a surface temperature for these gases that is Sorry, surface density of these gases, that's lower there.
Yes.
Yeah, my mistake. It's cooler during the day and hotter at night because of the thermal inertia that you're mentioning.
Right.
Yeah. By the same token, all those cooled off rocks right before dawn, they'll stay cold and heat up gradually.
Mm-hmm. Yeah, thanks, Rick. I totally misread that because I scrolled down and I didn't see Michael's comment about Tycho above. So,
Right.
so I totally missed
right.
it. Thanks for
Hey, Cesare, as long as I've got a little time here, if you go to again, back to the line plot showing the mass spec measurement with local time, or no, local time.
Yeah.
So I think you were trying to motivate that your code, I would have thought you were trying to motivate that your code, including diviner surface temperatures, would do a better job of explaining what was actually measured on the surface, but I'm not really seeing that here. So I'm sorry if I missed it. I guess I didn't understand.
Well, this is okay. These are all models again on this model. So there no, I didn't add the DNMS data here. So so that's a good point. Should I do also the DNMS to see if the density is follow this curve or this one?
But is there lace data shown on here?
No, it's these are all models.
Oh, okay.
Yeah, this is like from the paper from, I think from, oh, no, this is, okay, that's the lace means because I picked the lace location on my code. And so, yeah, this come from my code, but still the model. Yeah.
Okay, thanks.
I'm trying to remember, didn't the models have to do something weird to make the shape fit lace?
The Killian model, you mean?
I don't remember if Rosemary's did, but I thought at least some of the models got a steeper shape or a shallower shape or something that didn't match lace in shape. So you had to pick either the morning or the evening to fit. But I don't remember the details of that. And I was trying to do it in the background here and I did not find the right papers yet.
So, Michael, don't you think it's important to include like lace data in this model, even with this model comparison currently?
Yeah, I think we should get the lace and Laddie into here.
All right. So if there are no more questions, let's have another virtual round of applause for Cesare.
Thank you.
Very cool stuff. And so we have audible claps as well. Great. All right. So we have just under 10 minutes left. So the only other thing I wanted to talk about quickly was so two things, and feel free to respond to either of these. So one, Tim says Dave Williams at Goddard is working on restoring lace data, so that's awesome. But yeah, so I guess two things. One, folks who were at the European Lunar Symposium, was there any volatiles related highlights? I know I couldn't tune in virtually, but I know the abstracts are online. So any highlights from ELS, and then are folks planning on submitting abstracts to the Endurance Science Workshop, which I'm putting a link to in the chat? But the Endurance Science Workshop, just context for that. So Endurance is the long-range South Pole Aitken sample gathering mission that was highly prioritized as part of the Planetary Science and Astrobiology Decadal Survey. And so they're having a workshop to kind of, so the Decadal studied the concept and said, this is scientifically compelling and important, high priority. And so the workshop is planning to kind of just gather more community input on the concept And I think the next step from that will be to come up with some kind of report, and they'll use the report to form a science definition team. And so I wanted to bring that up in this group because self-polling and sample return in the mission concept study that was done for the decadal survey, there was, a lot of the sample collection objectives involve interior volatiles. So, things erupted from or things in pyroclastic deposits and, deep mantle samples that will tell us about the water content of the interior. And I think, something that wasn't necessarily part of the concept study, but, that's why I thought this might be good to pair with Cesare's presentation, but also, there's interesting exospheric science that can be done at the rover lander scale and looking at condensed volatiles and how those vary depending on slope and things like that. So yes, I was just curious if folks are planning on putting anything, and if not, or whether you are or whether you're not, I strongly encourage folks to think about what kind of volatiles related science, both the sample science is kind of self-evident and I think will be well represented, but also think about what sort of surface exosphere volatile science could also be done by a concept like that. But yeah, so two questions. Any interesting news from ELS, and what are people thinking for the endurance science workshop? Are you going? Are you submitting an abstract, etc.? And feel free to unmute or chat or raise a hand.
So I was at the European Lunar Symposium. It was a good, lot of presentation on especially European projects, of course, and Italian projects as well. But yeah, the pretty exciting new missions and works. Not only volatiles, but also like geology, etc. So yeah, it was a good meeting. Yeah, then for the new endurance, it's now that you mentioned, yeah, it could be a useful, interesting place for exospheric studies as well. I never thought about that, but until today. But yeah.
Yeah, I've been thinking about endurance the last week or two. I did not manage to write anything down yet, Parvati. So yeah, I'm still trying to pull together an abstract by the deadline tomorrow, but it's going to have a lot less time for community input and be a lot more just me trying to make a case of what I can think of, unfortunately. But yeah, I originally contacted Parvati and Carl, who I don't think is on, hoping that one of them already knew of something I could latch onto instead of having to lead it myself, but I'll lead it if I'm the person.
Yeah, and I think this is going to be the beginning of the process. So so I think there will be future opportunities to get involved. But but if it's a really compelling concept, and if it's the high priority robotic science mission of the next decade in that decadal time frame, then we should make sure volatiles are well represented. So yeah.
Yeah, what I've got in my head right now, kind of as an outline, is focus on the two things that can be done with a broad, like a spectrometer on a mass, kind of like Curiosity or Perseverance has, and without really necessarily saying what that sensing instrument is, but something that can, at a minimum, provide context for the samples that they're going to actually collect, so that we have the full geologic context, not just the mineralogical geologic context of samples. And then, some examples of what can be done when you have a multi-day mission like this, by looking at, especially if you're not moving during the night to preserve power, you've now got a evening and a morning, you can look at the same place in the evening and the morning and see how it changed. So those are the things I've thought of to put in the abstract so far.
Michael, something I haven't paid attention to until you mentioned it just now, is Endurance planned to be solar powered or MMRTG?
MMRTG, I believe.
Okay, so
yeah.
So it's just
Nuclear
staying warm at night, but not actually running. That's an interesting point.
I think that's
yeah,
the case regardless of the power source. I don't think they're going to be burning extra power when it's cold.
Yeah, but actually, I thought the plan was to traverse during the night.
Maybe I missed that. It's a hundreds of page long report.
Yeah, I need to look at that again. And I'll put the link to that in the chat in case folks want to take a look.
That is a good point with respect to Parvati mentioned that they're looking for interior water because it's geologists and they don't believe that atmospheres matter. And Cesare was pointing out that you're talking about adsorbed gases on the surface, and the standard operating procedure with using instruments like SAM on Curiosity is once they've got their sample, they shake it. And then they let it sit out, and I'm not quite sure what the aging purpose is, but typically ages overnight before they ingest the sample. So if you're looking for a representation of any adsorbed gases that might be at the surface at the time you sample them, the standard procedures that are used in mass spec work on surfaces would destroy anything you're interested in by modifying the sample.
They're trying to get rid of the air quotes contamination.
Right. But in this case, the contamination
is of interest to us.
Yeah. Well, in fact, I would argue maybe one of the most surprising and exciting things when you could find at the moon would be that potential contamination.
Right. And how does it relate to what they see when they actually do their microprobe or whatever of the samples to look for those interior volatiles? So is there actually any correlation between the remote sensing and the interior volatiles or not? Like, it hasn't been rigorously tested.
I mean, at League, we need to make a case for that, because the sampling protocol that you would use to capture a sample of unaltered surface would be very different from what they would use for drilling into a solid rock, for example, or modifying a sample for use with a mass spec on site. That they need something where they can capture it with whatever gases may be adsorbed on the surface and seal it immediately without mechanically altering it much.
So that's a slightly different test from what I was going to advocate for. Because
right now nothing exists, so we can advocate everything.
Well, they do have science questions in the report. So I was starting from the place of, let's not try and change their top level science questions that were evaluated in the decadal. Let's just say here's the right way to implement those science questions. So I'm not trying to add the exosphere or adsorb volatiles no matter how much I want to. I'm trying to say you need these instruments that, by the way, can do the exosphere or the adsorb volatiles, but that's not why we want them. I'm trying to make the case starting from their questions and working out rather than changing the questions.
Yes, good point.
All right, so we are 2 minutes past the hour. So I think we'll wrap it up for the day. But yeah, thanks everyone for dialing in. Thanks again, Cesare, for a great presentation. And we might not have a meeting next month because I might be on vacation. I'm not sure, I need to check the week, but we will see each other sooner or later. So take care, everyone.
Thank you. Bye-bye.